Let's start. If you have any question, ask me, okay? Simple harmonic motion. Before we discuss about simple harmonic motion, we have to understand harmonic motion. What is harmonic motion? Harmonic motion, it is a periodic motion. That means there should be a certain pattern. Like motion takes place in a pattern. During equal time intervals, it repeats its motion. Right? Before we discuss that one, before we discuss simple harmonic motion, we have to understand some terms. Period. What is period? Period is the time taken to complete one motion. That means if it repeat the same pattern, one circle, time taken to complete one circle. I'm not going to explain these things. I think you know these everything. Let's move to the simple harmonic motion. Simple harmonic motion, that means that there is a periodic pattern and the variation of the displacement. Right? Variation of the displacement always in a sine curve or cos curve. So there are several, there may be several curves like let's get just like this, right? So this is not a simple harmonic motion, right? Simple harmonic means there should be a simple, just like this, okay? Simple curve pattern. To get that simple curve pattern, we should have force. We call this one restoring force, right? This force, it is vary with the motion, but it takes a uniform path. It takes a uniform path. It moves in a uniform path, and there is a variable force act on it. And this one trying to drag this object, which is undergoes simple harmonic motion, drag to a certain point. We call this one center of the motion. Right? Always this variable force is trying to drag the object to the center, right? And the force, magnitude of the force is always proportional to its displacement, and hence acceleration of the object proportional to the displacement. And the force is always opposite to the displacement. Opposite to the displacement. Therefore, there is a opposite relation, but these are proportional. Acceleration and force proportional to the displacement, but opposite in direction. Let's see examples. This the spring. Real spring. If we get the real spring, this is this. If you consider this point as the center, this point as the center, it the concern the green colored dot, it moves across this one. The pendulum, it is very easy. Okay, let's start from this one. It comes to O. Again, it passes over and goes to C. Then again to O, and it repeats this pattern. It repeats this pattern. B to O, O to C, again C to O. This is one complete circle, and the time taken to complete that one is called period. Right? The time taken to complete, that's much. From B to O, O to C, again C to O, and O to B. Right, let's see this sun. If we push this sun, we apply force towards B, and it moves towards the B, and the displacement is increasing from O, okay? Therefore, it is opposite to the direction of the force. Now, can you understand this one? Right. Is it too fast? I can't get an idea. Can anyone talk to me? Can you understand this one? Right, let's move. We can so define simple harmonic motion. Uh, Motion which is acceleration is proportional to the displacement and opposite to the direction. So A is always proportional to minus x, and we remove this proportional sign using a constant k. We call this one is proportional constant. And you can understand the simple harmonic motion using a projection of a circular motion. Let's look at this dot. Right, it is performing this one circular motion, and this one is the projection of that one. Right, this one, when this one complete one circle, this projection start from this point to go there downward and again to the original question. Same here, right? So this dot complete circle, then completes a one circle. This one completes one periodic pattern. Okay. So if we consider this point P, which is moving with uniform angular velocity omega, right? The speed of this one or this one, if it is V, it is equal to the velocity component of this one, angular linear velocity component of P, right? Linear velocity component of P. It is, let's get, this is for the displacement, okay, not the velocity. Right, let's discuss displacement first. If this one here, OR, this is the displacement of the projection, the image of the particle, displacement of the projection. If it is OR, it is equal to A. A is the radius of the circular path. A sine theta, right? A sine theta. But we know, according to the circular motion, theta is equal to omega t. Just like S equals ut, theta equals omega t, right? So OR can be written as A theta O, A sine theta O, A sine omega t. So you can see x equals A sine omega t. The variation of the displacement is a sine curve. I have mentioned that one, right? This one, the black color dot, it's performing circular motion and the projection is red color. The variation of the displacement of red color dot is given by this curve, right? It performs simple harmonic motion and variation of the displacement is something like this. Then the maximum displacement is equal to the radius of the path, and it is A. We call that one amplitude. Right? We call that one amplitude. Then let's move to the velocity. Okay, velocity of the simple harmonic motion. Velocity of the projection is, as I mentioned, it is a component of the velocity of circular motion. If the velocity of the circular motion is u, you can write it as u cos theta. Right? Let's see. Here it is to this direction. Right? So it is u cos theta, not sin theta. It is u cos theta, and we can write cos theta in terms of a and x. What is a and what is x? This one is, this is a and this is x. So cos theta is, this is x and this is a. Right? Similar here, okay? So this is x and this is a. So the cos theta, you can write cos theta in terms of a and x as a squared minus s squared root a squared minus x squared over a. And u is a omega. What is this? You have derived this relation under the circular motion. And u is a omega, and cos theta is a squared minus x square root a squared minus x squared over a. So we can write v equals a omega. Instead of u, you can write a omega, and cos theta is square root a square v equals omega root a squared minus x squared. Right? This is the general relation for the velocity. General relation for the velocity. So if you want to gain the maximum velocity, the term a squared minus s squared should be maximum. Omega is a constant. You know, omega is a constant. So a squared minus s squared should be a maximum. The maximum, this value is obtained when x equals 0. That means the displacement is 0. That is the original point. Okay. Then it is a squared, and so we can write maximum velocity as a omega. The minimum velocity. Minimum velocity is obtained when this component is minimum. That means a squared minus x squared 0. X equals a at the maximum point. When the displacement equals to the amplitude, you obtain the minimum velocity. That is the maximum point. Right? That is the maximum point. Then the acceleration. Acceleration we can write as a component of the centripetal acceleration. A represents centripetal acceleration. So acceleration of the simple harmonic motion equal to the sine component of centripetal acceleration. Centripetal acceleration equals r omega squared. So instead of r, I put there a, so I write it as a centripetal acceleration equals a omega squared. If you substitute that one here, a equals a omega squared sine theta. A sine theta, we obtain this one as x. And this is opposite to the direction of the acceleration. So we can rewrite this one as a equals minus omega squared x. A equals minus omega squared x. This is the characteristic equation for simple harmonic motion. And this one is the characteristic equation for simple harmonic motion. A equals minus omega squared x. Then here, this is corresponding to the k we obtained earlier. Okay. So this is the general equation. If you are asked to show a certain motion is a simple harmonic motion, then you have to show that the acceleration of that object can be represented in terms of x with a constant. It means the acceleration of that should proportional to minus x. Very common questions, you are asked to show the motion of the simple pendulum is a simple harmonic motion. Motion of a string It's a simple harmonic motion. Then you should be able to show the acceleration of the object can be expressed in this way. A equals minus omega squared x. Omega can be any value or any uh, physical quantity, constant physical quantity. Right? You have to try this one. If you have any question, ask me. Okay. You have to try. You have to show motion of the simple pendulum is a simple harmonic motion, and motion of the spring, right? I have shown them at the second slide or third slide, the vertical spring and motion of the horizontal spring. All are simple harmonic motion. The examples for the simple harmonic motion, and you can prove that one, right? You can prove that one. Right? Is it too fast? Right. Can you understand this, son? Reply me. Let's move this part. Okay, phase of the simple harmonic motion. It is an angular term. That means it explains the situation of a particle. It explains the situation of particle. Let's assume the given particle, if it starts from point on the x-axis, right here. Let's start from the point, this point. Um, when t equals 0, it is here. When t equals t, it is here. At the same instant, if another object, p, let's get it as a, here. It starts from this point and it is m. So m start from this point when t equals 0. P is here and the sun is here. So it's at t equals 0, it starts from this point and it moves like this. Right? So there is a difference at the position of each object. This one is called phase difference. This is the phase difference. Phase is the phase difference expressed in terms of angle. This is the phase difference. So if we express this one as a sine omega t, here, this angle, this is phi. So this one is x2. X means displacement. Okay, x2 equals a sine omega t plus phi. Right? A sine omega t plus phi. If this one start from this point, there is a phi phase difference. Sorry, phi by two phase difference. So it starts, listen here. So there is a 5/2 phase difference. It starts from this point, right? When P start from this point, if there's another point, another object start from this point, it has 5 phase difference. So it moves like this, right? This is the phase difference. Mm. So if any object start from this point, what is the phase difference? Let's get this angle is 5. Now if it start from this point, it is omega t plus 5, right? It's okay. If it start from this point, then how do you write that one? It should be a sine omega t minus 5, right? A sine omega t minus 5. Here, phase difference of projections of the same particles. Same particle, projections of the same particles. Linear projection, horizontal projection and vertical projection, right? There is a 5 phase difference. Sorry, 5/2 phase difference there. Then energy of simple harmonic motion. Energy, when we discuss the energy, any object which undergoes simple harmonic motion possesses kinetic energy and potential energy, right? If you consider simple pendulum, it has kinetic energy and gravitational potential energy. Gravitational potential energy. Here, for the spring, it has kinetic energy and elastic potential energy. Okay. As we discussed earlier, at the initial point, at the center, the object has its minimum displacement and its maximum velocity. So at this point, its potential energy should be 0 and kinetic energy should be maximum, right? Kinetic energy should be maximum. When it moves upward, it decelerates. Right? When it moves upward, it decelerates. So the velocity is decreasing. Velocity is decreasing, then kinetic energy is decreasing. And the potential energy is increasing. But according to the conservation of energy, we know the total energy is constant. So when potential energy increasing, when kinetic energy is decreasing, that amount converting to the potential energy. That amount converts into the potential energy and maintain the constant total energy. When it reaches to the maximum point, it has maximum potential energy. It is in GH like this, and kinetic energy is 0. Then it comes to rest. Instantly come to rest and again start to accelerate down. The acceleration to this direction and the displacement is minus. Then velocity is increasing, but this h height decreasing. Then again, so it is a curve like this. Okay, but we know the energy is a scalar quantity, so there is no portion below the x-axis. Right. Displacement is a vector quantity, so you can denote the direction, right? Plus x and minus x, but the energy is a scalar quantity, so you can't draw this one below the line, below the x-axis. Okay. Let's see how you plot the variation of energy with time. The kinetic energy, when the displacement is 0, that when t equals 0, it has its maximum velocity, so therefore the maximum kinetic energy. This one is for something like this, okay? If it starts from this point, this varies, okay? Then it has a maximum potential energy and not the maximum kinetic energy. I am discussing about a simple pendulum which start from point A. It has the maximum kinetic energy when t equals 0 and then decreasing. When it reaches to its minimum value, the potential energy comes to its maximum value. And again, this one is increasing and this one is decreasing. So this is the variation of energy with time. Right? Energy with time. This is the total energy. Right? This is with time and this is with displacement. This is the total energy, this is the potential energy, and this is the kinetic energy. Right. We have to discuss the theories in a book. You have to discuss only these things, and you have to answer when you are answering questions. You can understand the lesson. Okay, I will give you a theory later. Now, try to graphically represent the physical quantities we discussed during this lesson. That means variation of acceleration with displacement. Try to plot that one. Variation of acceleration with displacement. Try to plot. I'll show that one, okay? Then variation of velocity with displacement. Variation of velocity with time. Try to plot. Variation of acceleration with displacement. A equals minus omega squared x. So A proportional to minus x. That means y equals minus mx. Variation is y equals minus mx. Velocity with displacement. And velocity with time. Velocity is displacement and velocity with time is acceleration with time. Acceleration with time. Displacement with time. Look at these things. When the displacement is equal to the amplitude in positive direction, acceleration It is opposite. So this is the variation with time. This one is for the velocity. Right. These are the graphs, okay? Hmm. Look at this one. This is the variation of velocity with displacement. Can you understand this one? It is parabolic graph. Right. Right. Theory part is okay.